Well, good morning there, physics students. Welcome to the last Wednesday of the year for my seniors. Wow, second last day for the seniors altogether. It's Wednesday, May 20th. All right, so today we're going to try to talk about torque. And we're going to try to learn how to set up and solve a torque problem. That's what we're after. And there's a couple of background concepts we got to get to. So let's start out with equilibrium. Equilibrium is used in a lot of ways. It comes up in science, a lot of things. Equilibrium in its basic form is that you have changes occurring you have opposite changes occurring at the same rate. There, I finally spit it out. In our case, we're talking about equilibrium as a motion. So what it means is that there's no change in the motion. So we have two states of motion that we can talk about. One is translation, where we move through space, and one is rotation, where we might not be going anywhere, but we're still spinning. So we refer to translational equilibrium and rotational equilibrium. So we've already kind of dealt with translational equilibrium. If there's no net force on an object, then an object keeps doing what it was doing before, right? That's Newton's first law. That's translational equilibrium. It doesn't change what it's doing, keeps doing what it was doing before. What we're adding in here now is this rotational equilibrium. Because an object there could be forces where the net force is balanced, but if the forces aren't acting on the same point, it creates a twist and it creates a rotation. And those are called torques. Twisting forces are called torques. So for rotational equilibrium, we have to have no net torque. We need to visit the concept of parallel forces. So I want you to imagine this meter stick here. Every little bit of this meter stick has mass, and every bit of that mass is affected by gravity pulling down. So every bit of this meter stick has weight. I could cut it into infinitely thin slices and say, well, this little bit has weight pulling down right there, and this little bit has weight pulling down there, and there, and there, and there, and there. But when all is said and done, you notice that I can balance my meter stick with a force just in one spot. So I can balance, I'm getting a little bit out of balance here. If I can balance all of those downward forces with just one force upward, well, what we can do is we can imagine all those forces acting from just one point. We can imagine all those parallel forces downward as if they were coming from just one point here. And then when I'm putting my force underneath, I'm supplying a force that's balancing all those. So here we have a wiener dog who's trying to level up. And we can picture that with this level, every single bit of this level has mass or weight. So all of these bits of the level are all pulling down due to gravity. But our wiener dog, this guy reminds me of my in-laws' wiener dog. His name's Longfellow. Good name for a wiener dog, isn't it? So all those forces are balanced by our wiener dog up. Okay? All those forces together. Now, I didn't draw this to scale very good. I'd have one big force downward. Okay? What's that point at which we can imagine all those forces? That's called the center of gravity, or also called the center of mass. It's the single point at which we can imagine all the weight of an object being located. So I have a center of mass. Okay? It's that point where there's as much mass above as below, to the left as to the right, and to the front as to the back. There's a point somewhere in me where I have my center of mass. If we have a nice uniform object like the meter stick, Well, the center of mass is right in the middle, right at the 50 centimeter mark. If I have something that wasn't imbalanced like that, I didn't grab something. Well, I do have one. Okay, I have this scenario. And you see that I have a meter stick balanced, and it's balanced at, just past the 90 centimeter mark, with a 500 gram mass out here at about the 97.5 centimeter mark. Oh, so how is this balanced? What we could look at is that the meter stick by itself would have a center of mass right around the 50. But this mass right here is balancing all that. The center of mass of the system is here. We're going to have to be able to understand mathematically this relationship. All right, so what's a torque? A torque is the product, means multiplied, of a force and its perpendicular distance to a pivot point. And I underlined perpendicular distance to a pivot point. That is defined as the torque arm. Okay, that length, that distance is called a torque arm. So I wrote an equation. Torque equals force times distance. I think we saw earlier that work is force times distance. This is different. Because in order for work to be done, the distance had to be in the same direction of the force. And in this case, this is a perpendicular distance. So this is not work. Okay, this is a perpendicular distance. So, all right, I got a door here, and it says my door is 0.85 meters wide, and I'm applying a force of 13 newtons right to this edge of the door, perpendicular to the door. What is the torque? Well, we can say torque equals force times this perpendicular distance. And so my force is just 13 newtons. And that perpendicular distance, well, that's the width of my door. The hinges are on the other side. I'm pushing on this side. So 0.85 meters. And we get 13 times 0.85 equals 2 sig figs. 11. Now what are the labels? Newtons times meters. Now, remember I said this isn't work. We're not going to replace this with joules. Okay? A joule is a unit of work or energy, and this is different. This distance was not in the same direction of the force. This was the distance perpendicular distance to where the pivot was. See, the pivot was over here where the hinges are. The force was applied over here, and this is a perpendicular distance. The directions don't work out. This is not energy. This is not work. And so we're just going to leave it in Newton meters, or sometimes you see it written in as meter newtons. That's a torque. All right. Maybe you've experienced this. You got a nut that's rusty, and you're trying to get it loose. And you put your wrench on here, and you apply your force. Gotta think, I almost drew my force in the wrong direction, and some of you are going to laugh at me because you say, Mr. Up, you're trying to loosen the nut, and you're actually tightening it. Okay, I caught it before I did it. All right, so I'm going to apply a force, and we've got some sort of distance here, right? Now, when I'm pulling on a wrench, depending on, how I can position myself, there's only so much force I can apply. Now, imagine, my torque here is going to be force times distance. What if my nut is just stuck, it's not moving? Well, what I might do is grab a bar and put it on my wrench. And now what happens if I apply my force? Now look, we'll call this my new distance, d prime. And so if I can apply the same amount of force, my torque is now going to be force times d prime. And even if it's the same amount of force, d prime is a lot bigger, so I'm going to get a lot more torque. The other thing is, you know, there's a proper amount of torque. What if I were tightening the nuts? If I were tightening the nuts on, say, the lug nuts on a wheel, you're ideally supposed to use a torque wrench. And the torque wrench is designed that once you get to a certain amount of torque, it's, I'm not sure if I'm using the right word here, but it's got sort of a clutch that will slip past, so you don't over tighten. You want them properly tightened, you don't want them over tightened. If I took my bar here and I tighten up these nuts, you're never going to get them back off again, or it's going to be very, very difficult. So you see that torque is a product of force and distance. To get more torque, I could apply more force, or I could apply more distance. Here's a couple doorknobs. Think about the doorknobs. All right, so it turns on some point in there, and I would apply my force at some distance from the center, right? Well, this doorknob has a center, and I could apply my force out here. You see how we got more distance? Plus, it's easier to grab hold of that. So like in schools and public buildings, pretty much all the door handles, I know I've got some closet doors in my room that still have regular doorknobs, but all the classroom doors have switched to a handle, and that's to make them more accessible. If someone doesn't have a hand that functions properly, doesn't have a grip strength, things like that, this is easier to apply a force to, and it gives you more torque for opening the door. Well, let's look at this. So we've got a support point here, and this young lady has a center of mass, I'm going to guess, you know, maybe about in there. And this guy has a center of mass, maybe about in here. His force is probably bigger than hers, I would dare say. But if they're in balance, this has to be in equilibrium. So maybe I should have done some different colors here. So we'll take her force times this distance has to equal his force times this distance, so that they're in balance. Now we know that the overall center of gravity has to be acting right through that line. That's the support point here. This is just trying to give a little intuitive approach to a torque problem without putting any numbers to it yet. Oh, here's one. If we look, we see that our support point is here, so there's an upward force. And then we think about, well, what's all happening here? Well, this bottle has a center of mass somewhere, okay? The roll of tape has a center of mass somewhere. The corkscrew has a center of mass somewhere. And so the product of this force and distance would have to balance this force and distance plus this force and distance. It's got to be balanced. Whatever's going on one side has to be balanced by whatever's on the other side of our pivot point, because it's balanced. It's in equilibrium. So that center point, that pivot point, has a name. It's called a fulcrum. And in diagrams, we often use a little triangle to represent our fulcrum. Now, some problems, like those last two, they have a definite place where you can see, all right, this is where we're going to provide our support. This is where the fulcrum is. In some problems, we're going to have a choice of where to put the fulcrum. So I want to work through a couple samples with you. Mr. Rupp, 1,350 newtons, wants to play on a teeter-totter with Bailey, 585 newtons. Just guessing, I hope I didn't offend you. The teeter-totter plank is 4.00 meters long. The fulcrum, this is a special teeter-totter. We can move the fulcrum to wherever we need it, okay? So if myself and Bailey are on opposite sides of this 4-meter-long teeter-totter, where do we want to put the fulcrum to achieve equilibrium? So let's do this as a problem. Now, torque problems are super critical to have a diagram. Super critical. And you can't make this tiny little diagram. You have to be able to read it and see things. Okay? Use some paper. Paper is cheap. It's a Wisconsin product. Help Wisconsin economy. So here's what I'm going to do. I know that my teeter-totter is 4 meters long. So I'm going to label that. I'm going to put my nice little brackets over 4.00 meters. Now I'm going to put in all the forces. Okay? So I'll put Mr. Rupp at one end. Okay, Mr. Rupp has a weight of 1,350 newtons. Okay? And we'll put Bailey at the other end. And she's got a weight of 585 newtons. Uh-oh. I forgot a piece of information for our problem, and that was the weight of the teeter-totter. Because the weight of the teeter-totter is going to be important in this. So let's see, let's say that the teeter-totter, the plank itself is 450 newtons, okay? And then we can think about where would the weight of the teeter-totter be? Well, the weight of the teeter-totter, let's imagine it's a uniform plank. So I would say that's right in the middle. 450 newtons. So I know this distance is 2.00 meters. All right. What I'm missing yet is my fulcrum. And I don't know exactly where to put it, but we're going to draw it in. And we know it's got to be closer to me than Bailey. Okay, so the fulcrum's going somewhere over here. And we have a torque arm between me and the fulcrum. Now remember, torques are always measured to the pivot point. So all of our torques are going to be measured to this. And if I don't know what a distance is, what do I call it? How about x? Well, if that distance is x, then what's this distance? Well, from here to here is 2 meters. So this would be 2 meters minus x, right? These are in meters. And what would be this distance? Well, that would be 4 meters minus x. Now, if you got to stop and look at that a little bit, do so. But everything's got to be measured to x, and we know the overall length. So if it's 4 meters from here to here, and this is x, well, this is going to be 4 meters minus x. 2 meters from here to here, well, this is going to be 2 meters minus x. Okay? So with that diagram, I have all my distances. If I make a tiny, tiny little diagram, it's not going to be useful for me to help figure out my problem. So here's what I'm going to do next. I'm going to say it's in equilibrium, which means that all of the clockwise causing torques have to equal all of the counterclockwise causing torques. What do I mean? Well, let's imagine that here's our fulcrum, and so we just pin it in place right here. What would, as we're looking at this diagram, what would my weight tend to do? Well, my weight would tend to make this thing rotate this way, right? My weight would tend to rotate it this way. That's a counterclockwise torque. I'll go ahead and label that. This is a counterclockwise torque. Now, what about the other forces? Relative to that fulcrum, this guy would tend to make it rotate clockwise. And Bailey would tend to make it go clockwise. So I'm going to use clockwise torques versus counterclockwise torques. Let's go through it. Let's set them up. So my clockwise torques, I'm going to have 450 newtons times 2 meters minus x. And that's, well, okay, and I've got another clockwise torque, so I'm going to add that to 585 newtons times 4 meters minus x. Okay, those are all my clockwise torques. Now I got to equal my counterclockwise torques, which is going to be 1,350 newtons times x. All I got to do now is solve my algebra. Solve for x. And I know you guys are capable of doing it. We might not like doing it, but we're capable. Okay? So I've got to distribute here. Okay. 450 times 2 is 900 Newton meters minus 450x. Okay. Plus 485 times 4. I better get a calculator. $1,940 Newton meters minus 585 newtons times x. It was Newton in here. Equals 1,350 newtons times x. Okay, so I'm going to combine like terms. So I'm going to add 450 newtons times x, and I'm going to add 585 newtons times x. I got to do that to this side. Plus 450 newtons times x, 585 newtons times x. So these are going to cross off. On that side, 1,350 plus 450 plus 585 equals 2,385 newtons times x equals, on this side I have 900 plus 1940, 2840 Newton meters. I'm almost there. So what do we got to do? Divide that side by 2,385 newtons. Divide this side by 2,385 newtons. Why did I write meters? That's a newton. Newtons are going to cross off. That's all going to cross off. Newtons are going to cross off. X equals 2840 divided by 2385 equals 1.19 meters. Now, I haven't been particularly careful with my sig figs as I've gone through this. I'm just trying to look if there's an easy place. I know this was 450 newtons. I'm just going to kind of guess that I was only allowed 2 sig figs on this. So I'm going to go 1.2 meters. I don't want to get bogged down on the sig figs rather than doing the torque problem right now. All right, 1.2 meters. Well, let's just double check. Where was my X? Oh, X is from me. So we better put that from Mr. Rupp. It looks messy, but it's really not, conceptually, it's not that bad. Let's take a look. I drew a diagram and I made sure I put in every single force, and I located my fulcrum and I put my distances in. Now, I didn't know where exactly to put my fulcrum, so that's my unknown. That's what we were looking for. Where would the fulcrum have to be? So I called it X. It was an unknown. Then I used this critical piece of information. Counterclockwise torques equals clockwise torques. I said, well, what are my counterclockwise torques? Just that one. What are my clockwise torques? Both of these. I plugged it in, and the rest was algebra. The rest was algebra. Okay, so here's another one. It says we've got a 2 meter long port swing. It's suspended from a chain at each end, and Nate, 755 newtons, is sitting 0.500 meters from one end of the swing. If the swing weighs 475 newtons, what is the tension force in each chain? So Nate and the swing are being held up by these 2 chains, but he's not sitting in the middle, so it's not equal on the 2 chains. One is pulling harder than the other. Tension is just a pulling force. Okay? It's just, when you pull with something, that's a tension. So I'm going to start out with my diagram. I got a port swing that is 2.00 meters long. There's a chain over here going upward. There's a chain over here going upward. I'm going to call this F. No, let's not call it F. I was going to call it F for force. Well, let's call it T1 for tension 1. Well, let's call this T2 for tension 2. Simple so far. Okay, Nate is sitting .500 meters from one end, and he has a weight of 755 newtons. And the weight of the swing, I'm thinking, we're not told anything else, so I'm guessing it's a uniform swing. I'm going to put that right in the middle. And that was, I should make it a little shorter by comparison, 475 newtons. And that distance from this end was 1.00 meters. That is my very careful diagram. I've got 4 forces, 2 upward, 2 downward. I know all my distances this time. Now, the next part, this is a critical piece of information. I have 2 unknowns. In order to figure that out, I'm going to have to use 2 equations, right? From your math class. If you got 2 unknowns, you need 2 equations. Here's my 2 equations. Clockwise torques have to equal counterclockwise torques. And the upward upward forces have to equal the downward forces. I could use my condition for rotational equilibrium, and then I could use my condition for translational equilibrium, because the port swing is not just flying off through the air. Okay? Now, where do I choose my pivot? And here's what you have to try to process. This swing is in equilibrium. So right now, as we're looking at, unless a chain breaks and Nate goes falling down, it's in equilibrium. And so therefore it's in equilibrium among any point. We can pick the pivot to be any point we want it to be. And here's where we have to be wise. I want to put the pivot either there or there. Try to think about why that is. I'll give you a second. All right, let me show you. I'm going to go ahead and put my pivot over here. And partly that's because I already drew my distances relative to this end. So I'm going to put my... No. Scratch that. I drew my distances to this end, so I'm going to imagine my pivot here. If my pivot's here, what is the torque caused by this chain? The torque is the force, which we don't know, T1, times the perpendicular distance to the pivot. The distance to this pivot is 0, which means the torque is right now 0. So one of my variables is going to drop out of the equation. And that allows me to solve the rest. If I put my pivot point in the middle, I'm going to have two unknowns. I can't solve an equation with two unknowns. If I put my pivot here, this one drops out. If I put my pivot here, this one drops out. You could do it either way. All right, I'm going to do clockwise torques and counterclockwise torques. So relative to that pivot point, this guy is nothing. This guy would be a clockwise, because if this torque, if I pin it here, this torque is pivoting it clockwise. This one is pivoting it clockwise. This one, pivoting it counterclockwise. Okay? Clockwise torques, I'm going to have 755 newtons times my distance to my pivot is 0.500 meters plus 475 newtons times 1.00 meters. Those are all my clockwise. Now it's got to equal my counterclockwise, which is going to be T2 times 2 meters. Okay? Easier than the last one to solve. 755 times 0.5. $377.5. I'll round off at the end. I know it should only have 3 sig figs. Newton meters plus, well, 475 times 1, which is 475 Newton meters, equals T2 times 2.00 meters. So I'm going to add these together. This says 852.5 Newton meters equals T2 times 2.00 meters. Divide both sides by 2.00 meters, and T2 is 426.25. I'm going to go ahead and round that now to its 3 sig figs. 426, the meters are going to cross off, newtons. There's my T2. Okay, so I just figured out this one was 426 newtons. Now, how can I get my other one? Now I have two options. One, I could literally now just imagine doing a new problem and assign my pivot point over here and then redo all my torques based on that and those distances. Or the simpler way is to use my second condition here. The upward forces equal the downward forces. So, oops, sorry about that. Let's talk about upward forces equals downward forces. Well, my upward forces are T1 plus T2. My downward forces are Nate, 755 newtons, plus the swing, which was 475 newtons. Now, we figured out the T2 was 426 newtons. So all I got to do is subtract 426 newtons from each side. And, you know, this is going to be all gone over here. So I'll have T1 equals 755 plus 475 minus 426. 804 newtons. So I go back to the top. T1, 804 newtons. Does that make sense? Yeah. Nate's sitting a lot closer over here. So this chain is holding more of his weight than if he were over there. All right. Now, it's two samples, one in which you had to find a distance. That one only had one place logical to put the pivot. This one had these two unknowns, so we had to do a little bit more with it. But I'm hoping that's going to help you out. I can do more examples, but it's just going to make a longer video, so I think I'm going to leave it. What are your questions? What do you need help with? So keep in touch. Let me know how you're doing.